to this lecture on process control, first order systems. This is the next part of first order systems. In this, we are going to solve a numerical on the response of first order systems. So we'll see the response of a first order system for some particular type of input. So let us see what is the question and what is the type of input. This question is from a previous year. This is a previous year question from GATE. A previous year question from GATE chemical engineering paper. This is in GATE chemical engineering 1992. The question is this: a thermometer follows first order dynamics with a time constant of 0.2 minute. It is placed in a temperature bath at 100 degrees Celsius and is allowed to reach steady state. Then it is suddenly transferred to another bath at 150 Celsius at time t equals 0 and is left there for 0.2 minutes. It is left there for 0.2 minutes. Then it is immediately returned to the original bath at 100 degrees Celsius. So you have to calculate, there are two questions. You have to calculate its reading, number one at t equal to 0.1 minute and also at t equal to 0.4 minute. So this is thermometer, first order, transfer function, k is 1 and tau is given as, time constant is given as 0.2. Now there are two temperature baths. Initially the thermometer is at this bath which is at 100 degrees centigrade, 100 degrees Celsius. It has been kept there for a long time so that steady state is reached. So the bath temperature is 100 as well as thermometer reading also will be, Ys also will be 100. So initially at steady state t less than 0, that is before the disturbance, xs and ys equal to 100. Now at t equal to 0, what happens? This thermometer is suddenly transferred to a bath which is maintained at 150 degrees Celsius. This thermometer at t equal to 0, is transferred to this bath. At t equal to 0, this thermometer is transferred to this bath. So the surrounding temperature now changes from 100 to 150. But it is how long it is kept here? Not permanently, only for 0.2 minutes. Only for 0.2 minutes. It is transferred to another bath and left there only for 0.2 minutes. Afterwards it is returned. Afterwards, after 0.2 minutes, this is returned back here. So this new temperature, new surrounding temperature of the thermometer is only for a period between 0 and 0.2. That is t less than, greater than 0 but less than 0.2. Now what type of input is this? The input for the thermometer, which is the surrounding temperature, changes quickly from 100 to 150 only for a period of 0.2 minute, and after which the input x returns to the original value 100. So this is t less than 0, this is for t between 0 and 0.2, and this is again back here for t greater than t naught. T naught or 0.2. T naught I is just using symbol, this t naught is 0.2. So this is what type of input? This is pulse input, right? This is going to be pulse input. How it will look? If you plot here x in terms of small x, x varies from, this is 100 to 150. Varies from 100 to 150 only for 0.2 minutes and then back to 100. So this is 150. All lines are horizontal and vertical, perfect horizontal and perfect vertical, even though they don't look like so. This is perfect horizontal. So this is t naught, this is at 0. So this is x. Now if you plot in terms of capital X is a deviation variable. What is that? X minus xs. And xs is what? 100. Xs is 100. So if you plot in terms of capital X, the deviation variable, that is x minus 100. So let us plot in terms of capital X and write the pulse input equations. So if you plot this in terms of capital X, which is x minus xs. The same graph, values will be 0 to 50. So capital X varies from 0 to 50 for 0.2 minutes and then back to 0. So this is a pulse input, and value of m, magnitude of m is, magnitude of pulse is 0 to 50, 50. So how do you write pulse input equation and pulse input response? How do you find pulse input response? First, how do you write pulse input? We had discussed earlier about the equations for pulse input. So you'll have two equations, one for this period 0 to t naught and then another one after t naught. So for t less than t naught, whereas t naught is 0.2 here in this question, the input equation is x of t equal to m into ut, and the response we have found earlier, yt equal to mk into 1 minus e power minus t by tau. So this has been discussed in my earlier lecture titled as PC40. The reference for this, link for this reference will be given above and as well as below in the description. How to find the response, how to write the pulse input equation, how to find the pulse input response. So for t less than t naught, the response equation is y of t equal to mk into 1 minus e power minus t by tau. The first question is you have to find the value at t equal to 0.2. Sorry, t equal to 0.1. T equal to 0.1 minute, yes. So that is less than this t naught. So you have to use this equation. So this is for t less than t naught. So if you substitute, simplify this, capital Y means y minus ys, m is 50, this is m, okay, this is m, k is 1 to 1 minus e power minus t, tau is 0.2, or y equal to, ys is how much? Ys we said, ys is 100. We found earlier, we told you earlier, the steady state output thermometer is, reading is 100, ys is 100. So 100 plus 50 into 1 minus e power minus t by 0.2. So if you simplify this, y equal to, if you simplify this, it is going to be 150 minus 50 e power minus t by 0.2. So this is the response equation. So this is the equation for t less than 0.2 minute. This is the response equation. This is the thermometer reading for t less than 0.2 minutes. The first question asked is what will be the thermometer reading at t equal to 0.1 minute. So you can use this equation and find what is the thermometer reading at 0.1 minute. So if you substitute t equal to 1 minute in this, sorry, not 1 minute, 0.1 minute in this, so I equal to 150 minus 50 e power minus 0.1 by 2. So the answer will be 119.67 degrees centigrade. So at 0.1 minute, the thermometer reading is going to be 119.67 Celsius. Now we'll go to the other period, t greater than t naught. What is the response equation for t greater than t naught? Discussed here in PC40. Discussed in my previous lecture, PC40. So what is the response equation for t greater than t naught? So let me write first the input equation. For t greater than t naught, the input equation is this. This is the input equation for t greater than t naught. And the response equation is this. So this has been discussed in detail in my previous lecture, as I said, PC40. This is the response equation. So if you simplify this, you can find the thermometer reading at any time t greater than t naught. That is any time t greater than 0.2 minute. Shall we simplify this? Y minus ys, m is 50, e power minus t by tau is 0.2 into e power t naught and tau are same. T naught is also 0.2, tau is also 0.2 minus 1. So this is equal to 50 into e power. So this is e power 0.2. This is e. This is simply e. So this becomes this term. So this term is e power 0.2 by 0.21. This is e power 1. E minus 1. E minus 1 is 1.72. So if you simplify this, this becomes 1.72 into 50, 85.9. So if you write, this is y minus ys, okay? Ys is being 100. So if you take y, so ys is 100 plus 85.9 e power minus t by 0.2. So this is a response equation for t greater than 0.2 minute. This is the response equation for t greater than 0.2 minute. Now the question is, find the value of thermometer reading at t equal to 0.4 minute. So all you have to do is substitute t equal to 0.4 minute here and then calculate. So substitute at t equal to 0.4 minute. You substitute t equal to 0.4 here. So I equal to 100 plus so this is equal to 111.62 centigrade. So this is the answer. So after 0.4 minute, the thermometer will read 111.62, and after first case, after 0.1 minute, the thermometer will read 119.67 Celsius. So these are the two answers for these two questions. Now I'll give you two more questions for practice. The first question A is, draw x of t, x and y on the same graph. Okay, draw x and y on the same graph. So how do you draw x and y on the same graph? X is simple. This is x. I mean, you plot in terms of small x, okay, actual variable. Plot in terms of small x. Anyway, the shape will be the same. Small x varying from 100 to 150. Now on the same graph, you have to calculate y and then plot. So how do you calculate y? For it, select some values of t from 0 to zero point 0.2 minutes. So for those values for t less than 0.2 minutes, you have to calculate y by this equation, by this equation, by this equation. Then select some values of t greater than 0.2, select some values of t greater than 0.2, and for those values you have to calculate y by this equation. Now for how long, how many values you will select, how long you will select after t greater than 0.2? Can we go on endlessly? So you calculate, you select t values such that there is not much significant change in y values. There is not much significant change in successive y values. For example, you calculate, for example, I'm telling, for example, let's say you calculate t for 1.5, and then also for t equal to 1.8 or something. If you find that there is not no significant change in y between these two values, you can stop. Okay, so select t values till such a value, till such time there is no further change in this small value of y. So you had set of two readings, one for t less than 0.2, this reading, these values, and one for greater than 0.2, these readings. But you have to make a single plot only. The plot will be single. The same graph you plot. How does it look? Y versus t. So both x and y on the y-axis, t on the x-axis. You plot both x and y on the same graph and see how does the response compare with the input. Now for t less than 0.2, this equation, t greater than 0.2, this equation. What about t equal to? T equal to 0.2. Give a thought, and when you do the calculation, you will know which is to be used, whether this equation or that equation for t equal to 0.2. So when you calculate, you will also know what is the minimum value of x, sorry, minimum value of y and maximum value of y, and what time it occurs. So calculate these and post your answers in the comment section below and let me know them. We'll see you with more problems in the subsequent class. See you.